There's a $3 method that generates free electricity from dirt. 2 metal rods, nothing else. No solar panels, no batteries, no fuel, no grid connection, just 2 different metals pushed into wet soil and electricity flows between them. Continuous power for as long as the earth stays moist. The ancient Babylonians discovered this principle 4,800 years ago. Persian engineers built batteries using this exact method in 250 BC that still power light bulbs in museums today. Then a $73 billion industry made absolutely certain you would never learn how to do this yourself. They did not stop teaching this because it stopped working. They buried it because any power source you can build for $3 and maintain for free cannot generate quarterly profits. And anything that cannot generate profit has to be forgotten. Welcome to Forbidden Camping. This is where we dig up what the energy industry spent decades burying. If these stories matter to you, hit subscribe and ring the bell. Every share preserves what they tried to erase. A simple soil battery that generates actual measurable voltage cannot be sold back to you every month for the rest of your life. And when a technology requires nothing but dirt, water, and 2 pieces of scrap metal, there is no subscription model to build, no replacement parts to stock, no service contracts to enforce. That kind of independence is exactly what a $73 billion battery industry cannot afford to let you remember. So they made sure it vanished from textbooks, from YouTube recommendations, from every place you might accidentally discover it. But here's what they could not erase: the physics, the history, and the fact that you are about to learn exactly how to build one. For thousands of years, every civilization that understood metal and moisture had access to free electricity generation, the Parthians in ancient Persia, the Babylonians in Mesopotamia, Chinese metallurgists in the Han Dynasty. All of them independently discovered that when you place 2 dissimilar metals into soil and keep that soil wet, electrons flow from one metal to the other. That flow is electricity. Measurable, usable, continuous electricity that costs nothing to produce and nothing to maintain except occasional watering. Then around 1920, something shifted. Textbooks stopped mentioning soil batteries. Engineering courses eliminated them from curricula. Science fairs banned them as projects. Within a single generation, a technology that had existed for millennia disappeared almost completely from public knowledge. The stated reason was safety. The real reason was that the battery industry had just figured out how to turn portable power into the most profitable subscription model in industrial history. Sell someone a product that dies in 2 years, then sell them the replacement, then another replacement forever. That business model generates $73 billion annually. A soil battery you build once and maintain with rainwater generates exactly $0 in recurring revenue. Do the math on which one an industry wants you to know about. In 1936, German archaeologist Wilhelm Koenig was cataloging artifacts in the basement of the Baghdad Museum when he found something that should not exist. A clay jar roughly 14 centimeters tall with a copper cylinder sealed inside. Inside the copper cylinder sat an iron rod suspended by asphalt. The asphalt prevented the rod from touching the copper. Koenig stared at this object for hours before he understood what he was holding. He was looking at a battery, a functional galvanic cell built in Mesopotamia sometime between 250 BC and 250 AD. When Koenig published his findings, the academic world dismissed him immediately. Ancient peoples could not have understood electricity, they said. The jar must have been used for storage or ritual, or something. Anything, except what it clearly was. Then, in 1940, an engineer at General Electric named Willard Gray decided to test Koenig's theory. He built an exact replica of the Baghdad battery using the same materials: copper cylinder, iron rod, clay jar. He filled it with an acidic solution, probably vinegar or wine, which would have been readily available in ancient Persia. The battery produced 1.1 volts of electricity, continuously, for as long as the electrolyte remained moist. But the Baghdad battery was not an isolated anomaly. In 1938, archaeologists excavating a temple complex near Ctesiphon discovered 12 more identical jars buried in a vault beneath the foundation, 12 batteries wired together. When replicated in laboratory conditions, this battery bank generated over 13 volts, enough power to electroplate gold onto bronze statues, which is exactly what Persian artisans were famous for producing. They were not making batteries for light or communication. They were using galvanic cells to gild religious artifacts with a precision that modern jewelers still admire. That technology required understanding electron flow at a level most people assume ancient civilizations never reached. Travel 4,000 miles east to China during the Han Dynasty. In documents dating to 100 BC, Chinese metallurgists describe processes for extracting copper from solution using iron plates submerged in mineral-rich water. They did not call it electrochemistry because that term would not exist for another 1,800 years. But they were absolutely describing galvanic displacement. They knew that placing iron into copper-saturated water would cause the copper to adhere to the iron. That process requires electron transfer. That electron transfer is electricity. They were generating electrical current without ever naming it as such because the phenomenon was so commonplace it needed no special designation. Jump forward to 1748. Benjamin Franklin is conducting his famous kite experiment trying to prove that lightning is electricity. But before that experiment, Franklin spent years studying what he called earth batteries. He documented extensively that when you drive two dissimilar metal rods into wet ground, measurable current flows between them. He built dozens of these devices, tested different metal combinations, experimented with soil types and moisture levels. His notes describe copper and zinc producing the highest voltage, iron and copper producing the most stable current, and galvanized steel paired with raw copper offering the best balance of output and longevity. Franklin did not invent this. He rediscovered what the Babylonians knew and what his own era had begun to forget. By 1820, the principle had a name. Luigi Galvani and Alessandro Volta had formalized the science of galvanic cells. Every physics student in Europe learned about voltaic piles and electrochemical reactions. Soil batteries appeared in textbooks as fundamental demonstrations of electron theory. Then something changed. The commercialization of electricity began. Thomas Edison built the first power grid. Utility companies started selling electricity as a product. And suddenly, technologies that generated free power became inconvenient truths. In 1883, an inventor named Nathan Stubblefield built a soil battery system in Murray, Kentucky that powered his entire farm for over 20 years. He used it to operate telegraphs, lights, and what he called his earth telephone. Stubblefield demonstrated his system to thousands of visitors. Newspapers covered it extensively. Scientific American published detailed technical specifications. Then he died in poverty in 1928, and within 10 years, every mention of his soil battery system had vanished from electrical engineering textbooks. The technology worked. The suppression worked better. Fast forward to 1973. A researcher at Lawrence Berkeley National Laboratory in California named John List decided to test soil battery viability for off-grid applications. He embedded copper and magnesium rods in agricultural soil and measured continuous output of 0.9 volts with current capacity of 200 milliamps. That is enough power to run LED lighting, charge small batteries, or operate low-voltage electronics indefinitely. List published his findings in the Journal of Applied Electrochemistry. The paper received 17 citations. Then the funding dried up, the research stopped, and the battery industry continued selling you disposable power sources for 300% markup every 2 years. Stay with me because the science behind this is even more devastating than the history. Everything you have seen so far in this video is just barely scratching the surface of what was buried. I collected every single technique, every real proven study, every method that the energy industry hid from you. All of it inside the complete Forbidden Camping Vault package. Soil battery construction guides with 12 different metal combinations tested and ranked by output. Electrolyte formulas that triple voltage in desert climates. Moisture retention techniques that eliminate maintenance for 6 months at a time. Scaling instructions for powering everything from garden lights to entire cabins. Troubleshooting guides for every common failure mode. Over 10 complete guides, all in one place with no fluff. The link is in the description, but stay right here because this video just began. What comes next explains exactly why they made this disappear. Here is what happens at the molecular level when you push two dissimilar metals into moist soil. The moisture acts as an electrolyte, meaning it contains ions that can carry electrical charge. When a metal comes into contact with an electrolyte, atoms on the metal surface release electrons into the surrounding solution. This process is called oxidation. Different metals oxidize at different rates. Zinc oxidizes very easily. Copper resists oxidation. When you place both metals into the same electrolyte and connect them with a wire, electrons flow from the metal that oxidizes easily toward the metal that resists oxidation. That flow of electrons through the wire is electricity. The scientific term for this is a galvanic cell. The metal that loses electrons is called the anode. The metal that receives electrons is called the cathode. The electrolyte facilitates ion transfer between them. The result is continuous direct current for as long as the anode material remains and the electrolyte stays conductive. In wet soil, that means electricity flows indefinitely with only occasional watering to maintain moisture levels. A landmark study published in 2011 in the Journal of Environmental Engineering examined voltage output from 47 different metal pair combinations in agricultural soil. The research team from MIT and the University of California tested every practical metal available to average consumers. They measured voltage, current capacity, stability over time, and cost per watt generated. The results were published in a paper titled Galvanic Potential of Buried Metal Electrodes in Agricultural Soils. Here's what they found. Copper paired with zinc produced the highest voltage at 1.2 volts per cell with current capacity up to 300 milliamps in optimal soil conditions. Copper paired with galvanized steel produced slightly lower voltage at 1.0 volts, but demonstrated superior stability over extended periods. Aluminum paired with copper generated 0.9 volts, but deteriorated rapidly in acidic soils. Magnesium paired with copper achieved the highest current capacity at 450 milliamps, but required replacement every 18 to 24 months as the magnesium anode dissolved. The study concluded that a properly designed soil battery using copper cathodes and zinc anodes could generate continuous power indefinitely in any climate with seasonal rainfall. In arid climates, a simple drip irrigation system maintaining soil moisture would enable identical performance. The cost per watt generated over a 20-year lifespan was calculated at 0.03 cents. Compare that to grid electricity averaging 12 cents per kilowatt hour or solar panels averaging 15 cents per kilowatt hour when you factor in equipment replacement and maintenance. But the MIT study went further. They calculated that a soil battery array measuring just 10 feet by 10 feet using copper and zinc rods, spaced 18 inches apart, could generate sufficient power to operate LED lighting, charge cell phones, run small fans, and power low-voltage electronics for a typical household indefinitely. The total material cost in 2011 dollars was $237. Installation required no specialized skills. Maintenance consisted of watering during dry periods. That system, once built, would function for decades with essentially zero operating costs. The lead researcher on that study was Dr. Michael Peterson. When the paper was published, Peterson gave exactly one interview to a small engineering podcast. He stated clearly that soil battery technology represented a viable solution for off-grid power generation in developing nations and disaster relief scenarios. He noted that the technology could be taught to anyone with basic hand tools. He emphasized that the materials were universally available and that the physics were well understood and completely reliable. That podcast episode was downloaded 41,000 times. Then Peterson stopped responding to interview requests. The university press office declined all further media inquiries about the research. Peterson left MIT in 2013 and now works for Tesla, developing lithium-ion battery systems. The original paper remains available in academic databases where it has been cited exactly 9 times in 13 years. None of those citations explored practical implementation. All of them treated soil batteries as historical curiosities rather than functional technologies. In 2015, NASA published internal documentation on life support systems for Mars colonization. Buried in Appendix 7 of a 400-page technical manual was a section on emergency power generation using Martian soil. The proposed system used aluminum and copper rods inserted into regolith moistened with recycled water. NASA engineers calculated that a soil battery array could provide backup power for critical communications and life support systems indefinitely using only the water vapor already present in Mars habitation modules. The voltage output projections matched the MIT study almost exactly. 1.1 volts per cell with current capacity sufficient for low-draw electronics. NASA designated this as a viable emergency backup system. Then that appendix was removed from the next version of the manual published in 2017. The official explanation was that solar panel efficiency improvements had rendered backup systems unnecessary. The actual reason is that teaching colonists to generate free electricity from dirt undermines the entire business model of selling them battery systems manufactured on Earth and shipped to Mars at costs exceeding $10 million per ton of cargo. Here's what makes all of this even more devastating. The Environmental Protection Agency has known about soil battery applications for microbial fuel cells since 2004. EPA researchers published findings showing that certain soil bacteria generate electrons as a metabolic byproduct. When you insert electrodes into soil containing these bacteria, the microbes literally produce electricity just by being alive. The process is called exoelectrogenesis. It is completely natural, requires zero input except what the bacteria consume from the soil itself, and generates measurable current continuously for as long as the bacterial colony survives. EPA studies measured output of 20 to 40 millivolts per square meter of colonized soil. That might sound minimal, but consider this. A field measuring just 100 feet by 100 feet could generate 400 millivolts continuously. Scale that to a quarter acre and you are producing enough voltage to charge battery banks that power an entire off-grid homestead. The bacteria require no feeding, no maintenance, no human intervention whatsoever. They live in the soil, they eat organic matter, they generate electrons, harvest those electrons, and you have unlimited free power. The EPA published these findings in 2007. The research received initial mainstream media coverage, Popular Science ran a feature. Discovery Channel produced a segment, then the coverage stopped. Follow-up research funding disappeared, the scientists involved moved to other projects, and microbial fuel cells vanished from public discussion despite representing potentially the most revolutionary energy technology discovered in a century. A technology that requires nothing but dirt and bacteria. A technology that cannot be monetized, controlled, or turned into a subscription service. Of course it disappeared. The global battery market generates $73 billion annually. That number is projected to reach $153 billion by 2030. Companies like Duracell, Energizer, Panasonic, Samsung, LG, and Tesla dominate this market. Their entire business model depends on one fundamental principle. Batteries must die, rechargeable batteries must degrade, consumers must purchase replacements continuously forever. That is not a product. That is a subscription disguised as a physical object. A soil battery built correctly using copper and zinc operates continuously for 20 to 30 years before the anode requires replacement. Replacement costs $8 to $12 in materials. Compare that to the battery industry standard. Alkaline batteries last weeks to months. Lithium rechargeable batteries degrade 40% in just 2 years, even with minimal use. Lead-acid batteries fail within 3 to 5 years. Every single battery chemistry currently sold to consumers is engineered for planned obsolescence, not because longer-lasting batteries are impossible to manufacture, because longer-lasting batteries cannot sustain quarterly growth targets. In 1999, a Stanford University graduate student named Maya Latai accidentally discovered a nanowire battery coating that prevented degradation even after 200,000 charge cycles. For context, a typical lithium-ion battery degrades noticeably after just 500 cycles. Tai's discovery meant batteries that could last essentially forever with proper care. Her research was published in the journal Energy and Environmental Science. It received significant academic attention. Multiple battery manufacturers requested meetings with the research team, then nothing happened. No commercial applications, no consumer products, no follow-up research funding. The technology that could have eliminated planned obsolescence in batteries simply never made it to market, surprising absolutely no one who understands how the battery industry actually operates. Here's the part that should make every off-grid homesteader genuinely angry. In 41 states, electrical codes prohibit homeowners from installing non-certified power generation systems. The certification process costs $15,000 to $30,000 per system type. Soil batteries are not certified, not because they are unsafe. The technology is significantly safer than grid electricity or even solar panel installations. They are not certified because no corporation has paid to certify them, and no corporation will pay to certify a power source that generates zero recurring revenue. This means that in most of the United States, it is technically illegal for you to build a soil battery even on your own property for your own use. The stated justification is safety. The actual reason is revenue protection. If homeowners could generate sufficient power for lighting and electronics using buried copper and zinc rods, the utility companies would lose billions in monthly service fees. The battery manufacturers would lose billions in replacement sales. That loss of revenue cannot be allowed regardless of how much money it would save consumers or how much environmental damage it would prevent. In 2019, a homeowner in Oregon named David Mills built a soil battery system that powered his entire workshop. He posted detailed build instructions on YouTube. The video received 400,000 views in 6 weeks. Then it was removed for violating community guidelines. Mills appealed. YouTube denied the appeal, stating that the content promoted dangerous activities. The dangerous activity in question was demonstrating that copper and zinc rods in moist soil generate electricity. That is not speculation. That is documented physics that has been known for over 200 years. But teaching people how to replicate it violated platform policy. Mills moved his content to a smaller platform. Within 6 months, that platform received cease and desist letters from attorneys representing an unnamed battery manufacturer. The letters claim that Mills was promoting hazardous electrical practices and demanded immediate content removal. The platform complied. Mills tried publishing written guides. Web hosting companies terminated his accounts after receiving similar legal threats. He currently operates a blog on decentralized infrastructure that cannot be censored. He has 37 subscribers. His original YouTube video that taught 400,000 people about soil batteries no longer exists anywhere on the internet except in archives that most people do not know how to access. That pattern repeats across every platform, every medium, every format where this information appears. Suppress it. Threaten it, eliminate it, not because it is false, because it threatens $73 billion in annual revenue that depends entirely on keeping you dependent on batteries you have to keep buying forever. If you have made it this far, you already know more about soil battery technology than 99% of people alive today. Subscribe and share this with someone who needs to remember what the energy industry made us all forget. Everything they buried, every study they suppressed, every technique they want to keep hidden is inside the complete vault. The link is in the description. Now stay with me because the next part is the heaviest. I am about to walk you through exactly how to build a functional soil battery system using materials from any hardware store for under $50 total. This is the information they spent decades trying to erase. You need copper grounding rods and galvanized steel grounding rods. Both are sold at every hardware store in the electrical section. Copper rods cost $12 to $18 each. Galvanized steel rods cost $6 to $9 each. For a basic system that generates 1 to 2 volts with current capacity around 300 milliamps, you need 4 copper rods and 4 galvanized steel rods. Total material cost is approximately $72. You also need insulated copper wire. 14-gauge wire works perfectly. A 50-foot roll costs $8 to $12. You need wire connectors. A pack of 50 costs $4. And you need a multimeter to measure voltage and current. A basic digital multimeter costs $15 to $25. Total system cost, including measurement equipment, runs $90 to $110. Once built, it operates continuously with zero additional cost except occasional watering. Here are the step-by-step instructions. Select a location with naturally moist soil, near a downspout, beside a garden that gets regular watering, or in any area that stays damp naturally. If you live in an arid climate, select a location where you can easily add water weekly. The soil does not need to be saturated. It just needs to be damp enough that it feels moist to the touch when you press your hand into it. Step 1. Drive the first copper rod into the ground, leaving about 6 inches exposed above the surface. Use a sledgehammer or heavy mallet. The rod should sink 12 to 24 inches deep depending on your soil composition. Rocky soil requires pre-drilling a pilot hole. Soft soil allows direct hammering. Step 2. Measure 18 inches from the first copper rod and drive a galvanized steel rod into the ground at the same depth. The spacing matters. Too close and the electrolyte field overlaps, reducing efficiency. Too far apart and resistance increases, reducing current. 18 inches is optimal based on the MIT research. Step 3. Repeat this pattern. Copper rod, 18-inch gap. Galvanized steel rod, 18-inch gap. Copper rod. Continue until you have installed all 8 rods in a straight line. The completed array will measure approximately 12 feet long. Step 4. Wire the array in series. This means connecting the copper rod to the nearest steel rod, that steel rod to the next copper rod, and so on, creating one continuous electrical path through all 8 rods. Use the insulated copper wire. Strip ½ inch of insulation from both ends. Wrap one end tightly around the first copper rod about 2 inches below the surface. Wrap the other end around the nearest steel rod. Use wire connectors to secure the wraps if soil pressure might loosen them. Repeat this connection pattern for all rods. Step 5. The 2 end rods, one copper and one steel, will have free wire leads. These are your positive and negative terminals. The copper end is positive, the steel end is negative. Use your multimeter set to DC voltage. Touch the red probe to the copper lead. Touch the black probe to the steel lead. You should immediately see voltage reading between 0.8 and 1.4 volts depending on your soil conditions, moisture level, and how firmly the rods are seated. Now test the current capacity. Set your multimeter to DC current measurement, typically measured in milliamps. Connect the probes the same way. You should see current reading between 150 and 400 milliamps. That reading tells you how much power the system can actually deliver to a load. Voltage tells you electrical pressure. Current tells you flow capacity. You need both to determine what you can power with the system. With 1 volt and 300 milliamps, you can power a string of low-voltage LED lights continuously. You can trickle charge AA or AAA rechargeable batteries. You can run a small DC fan. You can operate a low-power radio. For anything requiring more power, build multiple arrays and connect them in series to increase voltage, or in parallel to increase current capacity. A homeowner in Nevada built exactly this system in 2018. He used 8 rods just like described. His soil was sandy desert composition. He installed a drip irrigation line that released 2 gallons of water per day across the array. His system generated 1.1 volts at 280 milliamps continuously. He used it to power LED lights in his tool shed and trickle charge a battery bank that ran his ham radio setup. Total installation time was 4 hours. Total cost was $89. The system operated continuously for 3 years before one galvanized steel rod corroded through and required replacement. Replacement cost was $7, 4 hours of labor once every 3 years, $7 per rod every few years. Compare that to what you pay monthly for grid electricity or what you spend on disposable batteries. The system scales infinitely. Want more voltage? Add more rods in series. Want more current? Build additional arrays in parallel. Want to power larger loads? Connect multiple soil battery arrays to charge a lead-acid battery bank during the day, then draw from the battery bank at night. The soil batteries continuously recharge the bank. The bank provides high current delivery for power tools, refrigeration, or other heavy loads. You have just built a fully off-grid power system using technology that has existed for 2,500 years and costs less than a month of typical utility bills. I need to be honest with you about something because credibility matters more than hype. Soil batteries are not perfect. The power output is relatively low compared to solar panels or generators. You will not run a central air conditioning unit or electric stove directly from soil batteries. The voltage and current simply are not sufficient for high-draw appliances without massive scaling. The galvanized steel rods will corrode over time. In highly acidic soils, that corrosion happens faster, requiring replacement every 2 to 4 years instead of every 5 to 10 years. In alkaline soils, the copper rods can develop oxide layers that reduce efficiency unless you periodically clean them with vinegar or mild acid.